All right, welcome. In this video, I want to take a look at a couple more verification procedures. Just practicing with the techniques we're going to use to show that a problem is in the class NP. So, just a quick review here to start us out. If we have some problem like one of these ones below that we want to show as NP, we want to make a verifier, a verification procedure for it. And then just prove it's correct and show it runs in polynomial time. Now, if you're doing this sort of informally on the side, you just want to confirm to yourself that a problem is in NP, then you probably just do step one in hopes that your own, in building the verifier, you sort of intuitively confirm that it is correct and also polynomial time. But we're going to go and do all three steps and just make sure we confirm this for all of them. Now, I did want to do this for a couple problems here. Well, I've got three listed here. They're all sort of related problems. All three of these are NP complete problems, which we'll be able to finish off after a few more videos. But for now, we're just going to focus on showing that they're NP. I just wanted to go through each one in turn. Subset sum, I think, is exactly the same format as we encountered in a previous video. We're just given a set of positive integers, a target that we might want them to sum to, and then we're going to answer yes if there's a subset that of S that sums to our target integer t, and no if there is no such subset. So I think that was pretty much the way we had it before, except that this is sort of a pure decision problem variant in that the output is strictly yes and no. We can imagine a version of this problem where in the yes case we also want to know which subset sums to t. So here I've just got once again the strict sort of decision problem version where we have a yes no output. Then partition is again very closely related to subset sum, very almost a similar problem. A special case of the subset sum problem. In this case, we only have a set of integers. We don't have the target. Instead, we're asked specifically, can we split the set into two, partition it into two sets where the sum of each set is the same, equal sum. And there's more than one way we can sort of cash that out formally, but basically we're really solving a very similar problem as above, just where we fixed the target to be half of the total sum. So again, yes, no, I've got the pure decision problem version here. Yes, we can do it, or no, otherwise not caring how to do it if we answer yes. And then the last problem I've changed just slightly more, knapsack. In order to turn it into a pure decision problem version, we had to add an extra piece of input, which was the threshold, because the knapsack version that we encountered before was a strict optimization problem where we were trying to maximize our value. And so to turn it into a yes-no problem, we're going to add an extra piece of input, which will be our threshold value, which is we want to ensure that the value of all the items that we get is no longer maximum, but instead greater than or equal to our threshold. And we can sort of see that this problem and the original optimization problem are once again very similar problems and probably share similar resources if we want to solve them. All right, now we actually don't want to solve these particular problems. I mean, we might want to solve them, but my goal in this video is to instead try to build verifiers for them. So let's see if we can do that. I'm going to go ahead and start with subset sum. So let's do that. Okay, so to start out my verifier, I'm going to remember. So again, in the last video, we said, okay, to start out the verifier, we're going to use the same input that we had already. So I'm simply going to say, okay, this is going to be S and T, my set, S, my T, my target. But then in a verifier, we need to add an extra piece of input here as well. Now, what I name that extra piece, I usually give it the name P or C or W. Those are my go-to for proof or certificate or witness. Those are the three names we might give this extra piece of input that we're going to put in here. But before I go and grab one of these, I usually pick which one based on what I've already used. Here I've used S's and T's. That doesn't limit me in any way. I can pick any of these I wanted. So I might pick P or C or W, whichever one I prefer. But before I do that, I usually want to think a little bit about, well, what am I expecting here? Now remember, this extra piece of input, this is what we're asking from the all-knowing prover, the wizard. We want to confirm something. We want to confirm there is a subset that adds up to T. But how are we going to verify it? We need extra piece of information. What would that be? Well, what would make it easier? Now, when I say what would make it easier, I mean if we were not verifying the problem, if we were solving the problem, just trying to write an algorithm, then we actually have to find the subset that adds up to T. And of course, a good brute force solution there would just try all the subsets. And we saw that there's a dynamic programming solution that doesn't try all the subsets, but maybe tries a different technique. Now again, we're not trying to do that. That was a lot of work. We saw that that would take an exponential amount of work to try and do that, and maybe we don't have that much time. So what would make it easier if we got a little piece of extra information given to us? Well, that extra information that might help us, instead of having to try all of the subsets, what if they told us the subset that we should try? So here, I'm going to use W because I tend to favor W's. I'm going to use W for witness, and I'm going to say, I used a capital here because I wanted to say, what did I think this was going to be? I thought this was going to be the set that they told me about. Well, sets are usually using capital letters, not lowercase, so I'm going to say here W. I'm expecting W to be the subset of S that sums to T. Now, I've sort of verbally expressed that, but now I need to take what I just said and try and start building that into my verifier. So remember, my prover can give me anything they want here, and if I don't build it into my verifier, ways to rule it out, they're going to try and trick me by giving me something strange. So the first thing I should probably do is, I said we are expecting W to be the subset of S that sums to T. Well, I'm going to try and hash that out a little bit. I'm going to say, well, if W is not a subset of S, so if it is a subset of S, we're good, but if it is not, then we should say no. Okay, so what does that ensure us? And now when I'm expressing this, I'm sort of thinking ahead to my proof of correctness. Okay, so what do I know after this line? All I know is that W is a subset of S, which means, what have we ruled out? Well, they can't trick us. They can't give us sets that sum to T that didn't come from the original elements. So we're certain that it's a subset of S if we pass this test. But now we need more than that to say yes. We can't say yes yet. What else do we want to know? We want to make sure that the subset that we've selected actually sums up to our target. So let's see if we can calculate that. Let's calculate our sum. So if the sum of what? Now I'm going to say all the W's in W, lowercase w's in W, I'm going to add them all up. So that was a subset. Take all the elements in that subset, add them up. If it's equal to T, that's what we wanted. So if it's not equal to T, we'll say no. Okay, so again, follow me down the path. What do we know about W if we pass both of these tests? If it passes the first test, we know it's a subset of our set S. If it passes the second test, then we know if we add up all of the elements in W, that it must be equal to T. So now what do we know? Putting them together, that means there is a subset, W, of the original set S, that if we add them all up, it adds to T. Well, that's supposed to be our condition for saying yes. So say yes. Now, I mentioned that if we were sort of just doing this on the side to try and verify for ourselves, convince ourselves that a particular problem subset sum was in NP, we might stop here as long as we're confident that we've done this correctly. But to formally complete this, we should probably complete it with a proof of correctness. Now, I usually do these in 2 steps. I'm going to use a little shorthand here. I have yes implies yes here. I use this as a little code for myself for which theorem I'm trying to prove. This is really should say yes and do say yes. So what does that mean? That means if I should say yes, if there is a subset that sums to t, then I do say yes. Then I pass all my tests as a test and I get down here and I do say yes. So that's the first branch of the argument that I want to argue. So I'm going to start by assuming what I can assume from the antecedent here. I'll just say assume. I really want to say assume we should say yes, but I'm going to go further and say, well, when should we say yes? And looking over at the problem statement over there, it tells me if there's a subset that sums to t. So I start out my proof by saying assume there's a subset of S that sums to t. Okay, so again, that's what I get for free from just the antecedent. I'm trying to prove that if this is true, then this is true. So I'm starting out by saying, oh, well, assume this is true so that I can argue that this must be true as well. So that's where I am so far. So maybe looking ahead, what do I need to do? I need to say that I'm going to pass my test. So how can I argue that I passed my test? So the next bit I need to do is I need to say, well, what W is. Now remember, there's an asymmetry here. If we should say yes, then there need only be one W that makes me say yes, not all of them. There need only be one. So I'm going to say which one I think it's going to be. So I'm going to say let W be this set. So I'm going to continue my proof with the assumption that W is this subset that sums to t. Now, that should make it easy for me to say that I passed this test. So I'll say since W is a subset of S, it passed the first test. And since the next bit, we need to pass the second test. So what do we know about this? W is a subset that sums to t. So and since it sums to t, it passes the second test. We say yes. And remember, that's what we were trying to do. We're trying to argue that we say yes. So we argued that it passed our two tests here. Okay. So we've actually completed this branch. Now remember, what we're really trying to do is we're trying to argue a yes if and only if yes. Okay, now that goes both directions. We did that direction. We need to do the backwards direction. Now what that means is we can make an argument. Now here, I'm going to maybe split off. We've done the first one, it's done. I'm going to consider, let's go backwards. Let's see if we could do the backwards bit. So backwards has our arrow turned around the other way. That means we should assume we do say yes. So assume we say yes. Okay, so assume we say yes. Now this, I tend to find this reasoning a little bit backwards because we go backwards. So sometimes I feel that this is a little counterintuitive, and I like to do the other branch, but I'll show you that one in a second. Let's follow through on this one here. So assume we say yes. So since we say yes, W passed our two tests. Let's do the reverse argument of what we have up above here. Since W passed the first test, W is a subset of S, and since W sums to T, S must have a subset that sums to T. That was what we needed to prove. That's the conditions of when we should say yes. So now we've gone and taken that arrow and gone backwards as well. So this argument perfectly stands up fine, and I would certainly accept this as a proof. But I usually like to write this argument using the contrapositive. Now remember, if I negate both sides and I turn the arrow around, I get the contrapositive, which is logically equivalent and a logically equivalent statement to what I just proved. So I'm trying to do this this if and only if. We just did the first one up here. I just did this one backwards. That's down here. That's sufficient. Together, these are sufficient. But I'm saying I could replace this proof, if I don't like this backwards reasoning, with this no implies no instead. So let's see how that one works. So the no implies no means if I should say no, then I do say no. Okay, just like we had up here, except now I'm saying if I should say no. So let's start out assuming I should say no. So assume assume that S has no subset that sums to T. That's the difference from what we have up here, okay? A subset, there is one, to there is none. From there exists to there is none, all of them are not. It's another way of saying that, negating that exists statement. So now what we need to do is take this statement and argue that we do say no. That means we have to argue that in one of our tests here, we actually exit and say no. Now, again, from the last video, remember there's a strategy that we could take here. The longer strategy is saying, well, if he doesn't give us a subset, then we say no. So assume that the prover gives us a subset, then it must not sum to T. That's hopefully the argument we're going to make. And so we say no on this line. So we're going to actually do the slightly shorter one, which, as I usually suggest when writing this branch, just assume it passes all the tests except for the last one. So to set this up, we said assume S has no subset that sums to T. Now remember, in this branch, we have to make sure that all of the W's, that none of our W's are going to lead to saying yes. So every W has to be rejected. We have to say no in one of our two tests. So we can't assume which W we had like we did up above in this proof here. Instead, what we have to do is make sure our proof applies to any W, but we know that if we don't get a W that is a subset of S, we reject it in this first one. So I'm going to assume we pass the first test, meaning everything up till the end of this first test we can assume is true. So we will assume that W is a subset of S. So we assume that it's a subset of S, W is a subset of S, so that it passes the first test. Okay. But what do we know? We know S has no subset that sums to T, so if it passes the first test, if it's a subset of S, it must not sum to T. So we say no, and we're done. Now, you can pick whichever one you like when you're writing your proof. We have two branches we need to do. The first one sort of makes sense and is straightforward to me. I think this direction makes sense. I almost never turn it around, and I've never really seen any students in the past that would prefer that way. But when going the other direction, I definitely have seen individuals who prefer both directions. I personally like to go this way, and so for any future proof, that's the direction I'm going to go. But here I wanted to show you both directions, just so you have an example in case you want to tackle the other direction. Okay, before we do our next one, what I want to do is I want to actually look at, let's take a closer look here, at our second problem we have listed here, partition. Now, the reason I want to take a closer look at this is recognizing that the similarity between partition and subset sum are so close that hopefully we don't actually have to reinvent the wheel and do everything that we just did. And in fact, if we're lucky, we might be able to just go here and see, well, what changes could I make to the subset sum verifier that would make it a partition verifier? Well, remember we made this comment that the one thing about partition is we don't have a T. And that's because T has been replaced with something else. So we'll see this in a future video as well. In fact, I think we talked about this when we looked at dynamic programming. But in partition, our T is fixed. And it's fixed to something special. I should have left a little room out here. It's 1/2 of all of the S in S. So if you take your input S and you just add all the elements in it up, but then you take half of that, well then if you could partition your set into two equal sums, then this would be how much they would sum up to, because of course if you take two of these, they add up to the total. So what that means is we might be able to change this. Of course, here I'm just going to sort of do some surgery. Subset sum verifier, okay, let's call this partition. Okay, this partition doesn't get a T, but our W is going to be the same, except now instead of my T, that's where I'll take that value. Okay, and then it looks like probably in my proof down here, anywhere I've got a T, I need that value as well. Otherwise, I think the proof's going to work fine. Now, one of the reasons why I wanted to do this is, of course, I'm a little bit lazy. I didn't want to reinvent the whole wheel all over again. But also, a key tool in computer science is divide and conquer and code reuse, which is if you don't want to repeat yourself. You don't want to go over and do something again and again and again. So one lesson we're going to see in a future video when we start talking about reducing a problem to another problem, we can see that these two problems, partition and subset sum, reduce to one another in such a close way that they're really almost the same problem, or at least they have such close similarities that if we could find a solution to one, that solution usually works as a solution to the other. And that's sort of what I'm sort of pushing here by, instead of coming up with a new one, modifying that one. Okay, but let's go back and take a look then. For our third problem, knapsack, we don't have, it is still a closely related problem to both of these, in fact, and we'll again prove that in another future video. But right now, I don't think we can just grab our subset sum or our partition verifier and just assume it's going to work for knapsack with some alteration. So I'm going to say, why don't we tackle knapsack as its own problem altogether? All right, so let's get our knapsack verifier started, and it's going to take the same input as knapsack. So that's a list of weights and values. And then it's also going to have the capacity of our knapsack. And remember, for our decision problem version that we're going to consider here, we're also going to introduce t, our threshold value, as our additional input. That's the additional input to make it a decision problem. But we're actually going to have some additional input to make it a verifier as well. Now again, here's an example of a case where I've already used W and C, so P would probably be a good choice here. But in my problem statement over here, I already have a real good option for what my prover could give me, which is here it's my output condition is yes, if there exists this subset A, this index set, that's what we were calling it in previous videos, such that all this other business happens. Well, the costly part of knapsack is that we need to search for A, and there's exponential numbers of A. If, here's where the prover comes in, the extra power, if you could tell me my A, if you could tell me which A it is, then hopefully I can verify it myself. So I'm going to say, give me an A here. Okay, and again, capital because it's a set. All right, so my first type checking is just going to be to make sure that A is what I expect it to be. A is a subset of 1 to n. If it's not, then I'm immediately just going to reject it. If it is, and here's sort of a nice thing about making it a subset in this way, is that A will then select weights and values. Okay, and there's no way that they can mix us up by trying to get us to select a weight that's paired up with the wrong value, since we're really just selecting indexes into both of these. We're selecting items, not weights and values. So by selecting items, that A is now going to represent for us at least some collection of items. But remember, any old collection of items won't do. We want ones that fit into our knapsack and that are of enough value. So let's first make sure that they can fit into our knapsack. So if we have this sum, and again, you'll maybe notice over here, some of these criteria are listed right over here. So if we take this sum, and the way we're going to write this sum is over the indexes in A, we're going to take the weights and sum them all up, and they should fit into our knapsack, which means less than or equal to C. Of course, they should fit in our knapsack. But here we're testing for things that would violate that condition, so I guess I got that wrong. So let's instead say, if they're greater than C, that means they don't fit in our knapsack. We should say no. Okay, so that got our criteria for fitting in the knapsack, but our other criteria hasn't been handled yet, and that's going to be that we have enough value, that is, that we exceed our target threshold. So I'm going to say I We're the same thing set up. We're going to sum over all our i's, but now we're going to add up all their values. We want it to be greater than or equal to our threshold, so if it's less than our threshold, we should reject it. And now, again, think a little bit about our proof of correctness here. We're thinking, okay, what order, or sorry, after we pass all these tests, is this sufficient for us to say yes? And so usually at this point, I kind of run through. Here I know I've selected items, and if we go over here, it's a set of items, okay. They fit in my knapsack. That's the first one. They fit in my knapsack. And they have enough value, then it looks like I did everything on my output conditions over here for a yes answer, so that means I guess I should say yes. And again, that kind of verification means that when we write our proof up below here, we're good. Okay, also let's go ahead and I forgot to do this on the subset sum case, so that was an oversight. But I want to look at the runtime of these steps. Okay, so I want you to think about this yourself as we go one step at a time. How much time does it take to check to see if one set is a subset of another? You know, this depends. Hopefully you're thinking, well, it depends. How do we have our sets? And there are a number of different implementations of a set. But I'm going to assume here we're not trying to be too sophisticated. We've just got lists, okay, lists of elements. So checking to see if one list is a subset of another list, well, that's going to be about n squared in the naive case. Okay. Remember, we're not trying to look for anything super efficient here. We're looking for polynomial time only. If the operation we have in mind is exponential time, okay, then we might want to look for something more efficient. But we don't need to be looking for the absolute best in this type of analysis. So next up, adding up a bunch of elements, depends how many elements there are. Well, let's say there's n, and same thing here, order n. Okay. Now you'll notice that these tests are parallel tests we did in subset sum. So the same analysis would be true up there, which is definitely polytime. Okay, so we've got the p part, but we want to make sure it's correct, and then we'll show that this problem is np. So to do that, let's finish off with proof of correctness. Yes implies yes. And again, I'm going to do this here for my knapsack problem, so I'm going to assume that I have a yes instance, or that I should say yes. So what does that mean? Assume there is a collection of items, and I'm going to be strategic here, and I'm going to give it a name, but I'm going to call it A prime, because in a second I want to talk about what A is going to be. Okay. But I'm going to be very strategic by being very formal. And when I say a collection of items, I mean what? I mean this. Okay? Such that if you added up all of the items, all in A prime, if you added up their weights, it would fit in our knapsack. And if you added up all their values, it would exceed our target value. Now the way I've done this is very strategic and forward-looking, because I've actually just written off what the yes condition is written right here in my knapsack problem. Okay, we've just gone ahead and said, assume that it's a yes, and what does yes mean? Exactly this. Okay, there exists this thing. Okay, so now that I've got that, I'm going to push forward by saying, well, what about A? Well, I'm going to say, assume now that our wizard, our prover, gives us an A that is equal to A prime. Aha, they just give us A prime. Great. Now look, I also crafted my test to exactly mirror the definition of the yes instance, and the same thing I mirrored down here. So A passes all tests. So we say yes. Now this proof becomes quite easy because I've carefully worded each step to completely match, so that, you know, all you need to do is run your eyeballs over it to see, oh, that does match up exactly with that definition, and that does match up with exactly your wording down here below. Okay, now that's with a little bit of practice and having written this proof a couple of times. If you're doing this, don't expect it to pop out, you know, perfectly worded your first time. but maybe after a few times sort of massaging these words, you might be able to get it into, a nice elegant form like this as well. Let's do our other branch now. No implies no. Okay. This is the branch, remember, that I prefer. So I'm going to do this. So I'm going to assume that we should say no. Okay, so all I've done again in this step is take my and change it to a no, effectively. Assume there's no collection of items such that this is all true, that they fit in our knapsack and exceed our target threshold. So again, my strategy here is I'm going to tackle this problem by assuming I pass these two and then arguing that this last test is the test that we fail. So we'll assume that our set A that we're given is a subset of 1 to n, and that if we were to add up all their weights, it fits in our knapsack. So at this point, we're saying, well, okay, we know there's no collection that fits in our knapsack and exceeds our target threshold. So assume we get some collection of items that does fit in our knapsack, it must not exceed our target threshold. So the total value must be less than our target threshold, and therefore we must say no in our last step here. Okay. So we're done. We're done. We're good. We've finished that up. Okay. All right. So in this video, I tried to take a look at, we ended up looking at two different verification procedures for our two problems, and then noticed that our subset sum verification procedure could be changed into a partition one with just a little bit of massaging. Okay, that's all I wanted to take a look at in this video. So thanks for watching, and we'll see you in the next video.